Come on. With a common denominator. Keep it up for me. See how we roll. How the money comes in. The parade comes to town. Going down Broadway. It's a one-way street. Whichever way I go.
Hey everyone, my name is Zake. I do developer experience with ChainStack, and today we are building a Web3 AI trading agent, and we are doing it the hard way so we can learn. Let's go! Hey guys, as I'm editing this video, I realize that it might be a little bit weird to put out the shoutouts first right at the start of the video, so feel free to use the YouTube chapter navigation to skip around and to find what you need exactly. That said, I think the shoutouts here are pretty good, so if you're in no rush, feel free to check them out. Alright, let's get into these shoutouts. These are the individuals who helped me out by simply putting their work and insights out there. They weren't necessarily aware of how much they were contributing, yet the impact they've made is huge. So let's start. First up is someone not widely known, but I think he should be. He goes by the name Elnaril on GitHub. He's built an incredibly helpful Python library that decodes the Uniswap universal router calls. A real game changer for anyone working with Uniswap V4. It's called Uniswap Universal Router Decoder. If you've been around Uniswap V4, you know it's not exactly easy to interact with, even though it's singleton design and whatnot. So the fact that Elnaril has been pulling that weight is remarkable. And he's been doing this consistently for 2 years as well. So I'll link his stuff in the description. Definitely give him a look. Absolutely do a repo star and maybe buy a coffee. Next, I have to mention the creator who needs no introduction if you follow AI updates. It's Matthew Berman. He's been putting out frequent AI coverage on YouTube, and his channel has been exploding with good reason. He's technical, but also knows how to explain things in a way that keep you engaged. If you haven't checked him out, maybe swing by his channel and subscribe. Another person who deserves a shout out is Matt Williams, one of the folks behind Ollama originally, or a founding maintainer, as he calls it. Ollama is a library I genuinely and dearly love and use it whenever possible, even when I don't really need it. It's super practical, very neat, and we'll actually be using it here as well. We don't strictly need Ollama for the task at hand, but I'm such a fan that I'm slipping it in anyway. And then there is a non-technical channel worth mentioning. It's called Awakening Richard. Even though it's focused more on politics and current events in China, I want to credit him for the fantastic translation he did of an interview with Lian Wenfan, the person behind the DeepSeek model. Back when nobody really understood how DeepSeek worked, that translation shed a lot of light for me on what was up. And finally, though the list could be longer, there is the one and only Andrei Karpathy. He doesn't really need to be doing any of the stuff that he's doing, but we are all better off because he does. His deep dives into how large language models work are essential viewing for anyone curious about the tech. If you haven't already, stop right now and check out the video. I'm putting the link in the description. It's a masterpiece on how LLMs work and their intricacies. And that's it for the shoutouts. I'm grateful for all these creators and developers, and I hope this spotlight helps others discover their work as well. Let's move on to the next section, the setup, the stack, and what our agent pipeline is actually going to be. Alright, let's talk about the actual stack we are going to use and precisely what we'll be doing. We've got a few key objectives: experimenting with all the cool stuff like model fine-tuning and chain of draft and synthetic data, and in the classic Web3 spirit, also making sure we really own what we build. Web3 people love to understand and control what's going on under the hood, so we'll aim for as few abstractions as possible and we'll stay closer to the metal. Everything will be done in Python. Somebody recently asked me at a Web3 event I was attending here in Singapore, what's your tech stack for Web3 AI agents? And when I started listing things out, they were actually like, yeah, all right, that's enough, I get it. So here is our stack. We'll be running on a MacBook M3 with 18 gigabytes of memory. For as many steps as possible, we'll stay local. Again, because Web3 folks like to keep things in-house, custody of our keys, control over the environment, you name it. Whether you'd call that decentralization or something else, the point is we like to own it. So here is the plan. We'll build a Web3 AI trading agent in Python that operates on the ETH USDC pair on Base, the blockchain from Jesse Pollack at Coinbase. So hey Jesse, consider giving us a like. This agent will execute trades on Uniswap V4, and for the record, we are specifically focusing on the ETH USDC pool in Uniswap V4 for this tutorial to help Uniswap V4 with the numbers and to kind of make this tutorial a bit more advanced and fundamental. Uniswap V3, which is more popular and has better market penetration, is also a lot easier. So if you can do Uniswap V4, you can do Uniswap V3 for sure. So Hayden Adams, give us a like here for actually going the hard way. As for the stack specifics, we're going to use Apple's MLXLM library, which is designed to run natively on Apple Silicon. You can swap that out for something else if you're not on Mac. You can use something like Onslaught, but for me, that's how I'm keeping it local on the M3. We are deliberately avoiding the major frameworks like CrewAI, LangChain, ELIZA, or FetchAI, and so on. This time because our goal is to see how everything works under the hood, step by step, minimal magic layers. For the reinforcement learning part, we'll use Gymnasium, a maintained fork of the classic OpenAI Gym. And for anything too hefty to run locally on the 18 gigabytes of RAM, we'll offload to OpenRouter, which is going to be just one model for us. Honestly, the cost is going to be tiny, maybe pennies, probably under 10 cents for the entire setups, and definitely under 50 cents. You can bet on that. We'll also use Foundry to fork the base mainnet, and we will of course use the free tier chainstack base nodes to access the chain state, the best base nodes on the market, and I mean the best. I'll walk you through the actual implementation details in the next section, and then we'll start going step by step. As always, all the code documentation and step-by-step breakdowns are linked in the video description. It's all Python, it's all open, and I highly recommend actually watching how it's done rather than just skimming the docs. So let's dive in. And by the way, I found the base community to be very welcoming and positive, so good job there. So how do we actually go from this to this? Now that we have outlined our stack, let's talk about the actual pipeline. We'll roughly trace the Web3 progression as an industry with our tutorial. From the perspective of this video, the industry in general went through 3 distinct stages, or at least 2, and is currently going through the 3rd one. It all started with the manual one-off trades like people used to do, and in quite a bit of cases still do. Over time we saw an era where bots took over, especially around the DeFi summer unlocked by Uniswap. That was when it became the most evident. The MEV, or maximum extractable value, was kinda discovered and then productized, and it made automated strategies ubiquitous. It was a shift from a fully manual trades to heavily scripted bots. I believe the next phase is the AI agent era in Web3 that's starting right now. So here's our plan. First, we'll perform a swap manually, then replicate the same swap in a bot script. A simple routine to do ETH to USDC and USDC to ETH swaps on Uniswap V4 running on the base blockchain. Once we have that script handling one-off trades, we'll progress to a full agent implementation in several stages. You don't need to replicate each stage in your own workflow, but we'll stack them one after another so we can see how everything fits together. We'll be using a fork of the base mainnet that we create with Foundry to do the trade, so you can experiment as much as you want. But honestly, the transaction fees on the base mainnet are so low, and the ETH-USDC pair is not as volatile as lower cap coins, so you can do our simple tiny trades right on the base mainnet. It's good to learn, however, how to use Foundry, which is an amazing, sophisticated, and very easy to use and reliable tool. So I suggest that you do, and we are including it. Then we'll use the script to create a stateless Uniswap V4 agent that uses Ollama to make trade decisions on the ETH-USDC pair. It will be called stateless because it's not going to keep the memory in between the trades. It's going to use any local Ollama model that you can plug in and run locally on your machine. And we are going to use the latest FinR1 model for this. which is a DeepSeek R1 model fine-tuned for finances and was released recently as of this video. Then we'll proceed to creating a stateful agent that's going to skip all the reg, CAG, CAG, and all the typical retrieval augmented generation stuff, and still going to be a stateful agent because it's going to be retrieving the data directly from the chain. I mean, blockchain is an append-only DB at the end of the day anyway, so we don't need any of the fancy vector DBs for our case. It's going to be a stateful agent because it's going to keep all the trade data between the trades for as long as it goes. It's going to be pretty cool. Next, we'll fine-tune an agent on the same real data it's running on. We'll collect the raw Uniswap V4 ETH-USDC pair data on the base mainnet chain, then run it through a GAN or generative adversarial network to create synthetic data, possibly introducing volatility to better train the agent. With that synthetic data, we'll do the teacher-to-student distillation between two open-source Chinese models, QWQ and Qwen. We'll use this specific QWQ-Qwen combination for fun, and because they both come from the same company, Alibaba. And also because QWQ, which has 32 billion parameters, drew a lot of attention when it launched, and Qwen is a smaller model at 3 billion parameters. You can run it locally on your MacBook, on most MacBooks. It's very, very light. We'll follow a paper on generating synthetic data, and we'll also implement a chain of draft approach to optimize token usage, which is effectively just a prompting strategy and is yet another paper. We'll then use LoRA or low rank adaptation to produce our first fine-tuned model that creates a delta between the base Qwen 2.53 billion model and our specialized agent knowledge. We'll plug the model using MLXLM into our stateful trading agent and let it run on our base mainnet Foundry fork. As a fun example, we'll add a reinforcement learning step on top of the fine-tuned model to push the performance even further. It's going to be simple but very quirky example because we are going to take our custom LLM delta fine-tuned on the synthetic data and stack on top of it yet another fine-tuning, which is a very shaky and brittle combination, as you will see. Finally, we'll test it all by fusing our fine-tuned model delta and converting that to an Ollama compatible format and plugging the resulting Ollama based model into our stateful agent so it can execute trades. And this will land us at about where we started with the agent implementation, although it's going to be a full agent on our custom LLM this time. There's going to be some other fun stuff in there as well, like agent canary rewards. So let's go. Okay, let's do a simple Uniswap V4 swap on the ETH-USDC pool on the base mainnet manually and use MetaMask. Here's a quick one. And now onto the script itself, our first one. Let's do a quick overview of the Uniswap V4 architecture first. At the core of Uniswap V4 is this singleton concept. Instead of having many separate pool contracts for each token pair, there is essentially a single overarching pool manager contract that keeps track of all liquidity positions using unique pool IDs. That design allows for a central place that orchestrates everything from provisioning liquidity to executing swaps and collecting fees. All the logic lives in that one major contract, plus a few external hooks and the different liquidity pool IDs derived from the contract data like token 0, token 1, fee tier, and hooks. All the Web3 folks know this. It's a more unified system compared to the earlier, much easier to handle Uniswap V3 versions. But because V4 can introduce extra functionality via hooks, you can effectively spin up ephemeral or specialized versions of these pools without needing a dedicated contract for each, like the liquidity pairs that we used to have. Once you have that pool ID, you can reference, however, it anywhere for retrieving the state reading or writing liquidity and definitely for swapping. Now let's do the script to replicate this swap. In our project, we have this config.py file storing all the essential parameters. The base RPC endpoint, the private key, the token addresses like USDC and wrapped ETH address, and the universal V4 address. Uniswap V4 uses this universal router on base to route the trades, so you don't have to juggle multiple router contracts. Everything is rolled up into a single aggregator. There seem to be tons of other custom routers deployed, but we are going to use the official one. Check out the USDC to ETH swap.py script and the reverse one, and inside we import the environment variables from the config, set up a Web3 connection to the base RPC, and load the contract ABIs for any tokens or pool contracts we need to call, which in our case is the ETH-USDC pool. And step by step, the script does the following. It initializes and checks the balances where we connect using our private key to get the account we'll use for signing transactions. Then we check how much USDC and how much ETH we currently hold on Base. That helps us confirm the script is working, and we see the before and after states. Then we construct all the necessary swap data using our favorite Uniswap universal router decoder library from our favorite dev LNRL. Then we do the token approval, and by the way, if there is any non-Web3 folks watching this in confusion at this point, go ahead and play around with the code. Hands-on is always easier to understand, I find. Then we build the swap transaction. Then we broadcast and wait for the transaction confirmation, and we are of course using the chain stack base nodes for this, the base nodes on the market. And we are done. We have our first script to do the swaps on the chain. There is also an optional, at this point, fetch pool data diagnostic script that you can run to check the pools, and we'll be using this later as well for the actual data fetching from the chain for the agents to act on. So that's the overall flow. We rely heavily on the Uniswap V4 pool manager's architecture, a single place to handle pools, hooking in a universal router for the swap and letting us pass in the right pool ID for our ETH-USDC pair on Base. The code references might look dense, but it's mostly about constructing these calls to the router, passing the right parameters, and letting the underlying V4 logic do its magic. And alright, let's move on to the agent. Now let's implement the Stateless agent. Let's start with a quick overview of Ollama. Ollama is basically an inference agent for LLMs, so you have a model in GGF format. Ollama can serve it on your own local machine without connecting to any external APIs, which is great for our case. It's lean, fast, and designed to handle large context windows, which is perfect for what we were building. And it's also my favorite local LLM tool. In our case, we'll be pulling in the GGUF version or GOOF version of the Fin R1 model from Hugging Face. This model is a fine-tuned financial model geared towards predicting or analyzing trading scenarios, and it made quite a splash recently when it was released. It's using the DeepSeek R1 framework to create a financial model based on the Qwen 2.57 billion instruct model. Incidentally, a similar model to the one we'll be using later in our tutorial. We'll be using Qwen as well, although our version is going to be a smaller model with 3 billion parameters, so we can run it locally. It's going to be a more chaotic base model. I again suggest at this point watching the Andrei Karpathy video on the LLM's deep dive on the difference between base and instruct models. But what it means for us as TLDR is base models is the raw version, and instruct model is what most people use, and the one that's gone through labeling, supervised learning, and numerous other fine-tuning techniques to stay coherent. By running the Fin R1 model through Ollama, we can generate trading decisions locally without having to rely on a cloud endpoint, which is what Web3 is all about, by the way. Now let's do a concise walkthrough of the code architecture and see how it all ties together, and especially the rebalancing component. Also, now is a good time, by the way, to spin up Foundry. And Foundry is everyone's favorite Web3 development framework that streamlines building, testing, and deploying smart contracts on EVM-compatible blockchains. It's by Paradigm 2, a very well-known Web3 company and a VC fund that contributes a lot to the ecosystem. We'll use Foundry to fork the base mainnet. When we talk about forking an actual chain with Foundry, we are referring to creating a local copy of that chain's current state. In this case, if you fork the base mainnet, Foundry spins up in an environment that mirrors the exact contracts, balances, and on-chain data from base at the moment of forking. Under the hood, Foundry queries a node, a chain stack node of course, for the latest block information and replicates the block state in a local simulation. So now you've got a private playground. It's as if you're interacting directly with the base mainnet, but you are doing it all from your own machine. Running scripts on the forked network follows the same routine as it would on a production network, except here you have full control. You can use various cheat codes and whatnot. Since the fork holds the real chain data, you'll see precisely how your contracts behave with the actual balances and code that exists on base. Except we are not using any contracts. Our contracts, we're using the ETH-USDC Uniswap V4 pools and contracts. So forking base with Foundry gives you a precise and malleable clone on the mainnet environment, lets you experiment quickly and validate your assumptions without ever touching the actual chain. So now let's talk our agent script. We have three main pieces: config.py. This file defines most of our environment variables, contract addresses, and settings. For our instance, it specifies the default Ollama model in the Ollama model variable points to the local RPC URL, holds our trading thresholds, and sets up a key detail, the rebalance threshold, which is very useful for us. It also includes a flag to switch between the MLX-based models and the Ollama-based models, and we're going to be using MLX for fine-tuning later. And for now, we'll focus on the Ollama path. And then it has the Uniswap V4 swapper.py script. This is the script that interacts directly with the Uniswap V4 contracts on chain or on the Foundry fork. In our case, doesn't really matter. If we need to swap ETH to USDC or vice versa, or we want to retrieve the current ETH price from the pool, it's all happening here. The swapper does the heavy lifting of building and sending the right transactions to the universal router, plus managing approvals and error handling. Whenever the trading agent decides it's time to rebalance or open a position, it basically uses our previous swap ETH to USDC or swap USDC to ETH scripts here, the ones that we completed in the previous chapter. Uniswap V4 stateless trading agent. This is the main orchestration logic, a stateless agent that queried the Ollama model for trading decisions. Inside you'll see a function that gathers market data using the fetch pool script, which we previously mentioned as well, that you can set up however you want. For example, you can poll the pool every few seconds or on the state of the pool and transactions, and the ETH USDC exchange rate, which is effectively the ETH price, is gathered over the last, for example, 5 minutes and your ETH USDC portfolio balances. And then the script packages everything into a prompt for the LLM, for our Ollama model. The FinR1 model loaded with Ollama is then asked, do I buy or sell and how much in that context? The code then interprets the response, executes the right swap, and logs what happened. Yes, it's that simple. We call it a stateless agent because, once again, it's not keeping track of how we are doing between the trades. Every trade is a new trade for our agent script, and it's a new question response instance to the FinR1 model. And every time a trade is made, you can actually see the transaction on the Foundry Anvil fork, and you can run a cast call to see the trade details and verify. Check the docs and the code in the repo. It's going to be much clearer in the Chainstack developer portal for all the complete details, and play around with this. A big part of our agent script is how we handle rebalancing. So if the ratio of ETH versus USDC in the portfolio drifts too far from our target allocation, which we set 50% ETH and 50% USDC, and I'm going to explain later why, then the agent performs the corrective swap to move us closer to that target. The logic is that if ETH pumps and we end up with way more ETH value than we intended, we'll convert some of it into USDC, and if ETH dumps, we might go the opposite way. This way we lock in the gains and keep risk in check. It's a fairly well-known rebalancing logic, even though it's usually not set at 50%. Specifically, the agent checks the current portfolio composition, compares it to the default ETH allocation, and if the difference exceeds rebalance threshold, it triggers a trade. That's basically the why of rebalancing. We want to maintain a predetermined risk profile rather than blindly letting the portfolio run all in on one side. We set it to 50% in the config file to effectively make the script query the FinR1 model or whatever you have plugged in through Ollama on every trade, instead of executing the trades as a bot. Because if we set it to a different parameter, to different percentage, there's going to be a few trades the bot does without asking the model because of how we set it up. So 50% makes it effectively almost always ask the Ollama model on the trade. So how it all runs: you have your local environment with Foundry for a testnet, start Ollama with your GGUF FinR1 model, so it's serving locally, fire up the trading agent script with Python Uniswap V4 stateless trading agent.py. The code calls Ollama, passing relevant market data, for which we're using the fetch pools script, ask the FinR1 model for a recommended action. If rebalancing is due, and for our purposes we make it always due with the 50% rebalancing threshold, and if the LM sees an opportunity to trade, the script uses Uniswap V4 swapper.py to execute that swap. That's all we need to get the big picture. Ollama plus FinR1 for local LLM-based decision-making, Uniswap models for the actual swapping, and rebalancing logic to keep the portfolio aligned with our target allocation. And congrats, you have your own first completely autonomous local Web3 AI trading agent built by you. And did you see any of the abstract framework stuff where you have no idea or control of what's actually going on? No. Is your agent secure? As secure as a non-LLM script can be. No one can talk to your model and get your private key. No one even knows there is a model. And the model itself has no idea it's part of an agent. And if there is any private key, it can give it out. The only external API you are using at this point is the chain stack base nodes one. That's it. Easy, secure, transparent, and again, very easy to understand. Congrats again, a few minutes into the video and you are already in the top 10% of understanding Web3 AI agent. Nicely done. Alright, now let's talk about the evolution from our stateless agent to stateful agent version and why we would even bother with this extra complexity. It's because we obviously want our AI trading bot to remember things like past trades, performance, strategies, so it can adjust future decisions accordingly. We still rely on the same Ollama FinR1 model for our local LLM-based decision making, but now we track and store critical information between trades, gather metrics on what's working and what's not, and keep a handle on the overall strategy. So how does that happen in code? I think it's pretty cool, as we are kind of doing reg or retrieval augmented generation, but also not really, as we are not bothering with any of the vector DBs or any DBs for that matter outside of the blockchain itself. We are working solely through the context window, and I just love how Web3 and AI fuse perfectly together a lot of the times, and it's just one of those. So okay, let's jump right into the code or the logic. First, the stateful agent imports everything from our earlier stateless agent. Recall that the stateless agent had a pretty straightforward loop. It would fetch the latest market data, pass it to the LLM via Ollama in our case, parse the LLM's recommendation, buy or sell, and then do a swap accordingly. That was effective enough, but it didn't know how much we had fared after each trade. Every time it saw a new prompt, it was as if the agent had an amnesia about its previous decisions. Now, the stateful agent is different in three major ways. One is maintaining context in memory. We have a class called trading agent. It keeps a running log of the market states like is price, volume, volatility, trading decisions like LM decision or rebalance threshold, and the performance and rebalance actions and performance metrics such as profit, loss for each category of trade. This context is basically our agent's memory. Each time we make a trading decision, whether it's from the LLM, from a rebalancing rule, the agent records the result. Did it succeed? How much profit or loss did we realize? And so forth. Later on, it can compute broader performance metrics from this data. Two is longer-term strategy. The agent can define something like a current strategy, how long it should run, and how well it's performing overall. For example, you could say, let's adopt an LLM-based scalping approach for at least 30 minutes or like up to 24 hours or longer. The code keeps track of when we started the strategy, how long we've been in it, and whether we should continue or pivot to a new approach. This is all governed by the trading context storing the time we began, our chosen direction, how well it's going, and then summarization and context window management, which is a very important and pretty cool. Large language models have finite context window, as you know. So we keep appending more and more messages or trade logs, and eventually, if we keep doing this infinitely, we'll overflow context window capacity. To handle this, the stateful agent keeps track of the current context window token consumption, and then when it's close to, for example, 90% threshold, which means the model has consumed most of its context window, it does a summarize and restart context action. So essentially, it'll compress the conversation or results. So far, hold on to the key pieces of intelligence like the average P&L, last successful trade, or overall strategy, and then wipe away the heavy logs. This keeps the conversation going without the agent drowning in the weight of all prior messages. You can use the threshold in any convenient way possible. For example, if you find your model tends to hallucinate long before hitting the context window limit, you can set the model to summarize and restart on, for example, 50% threshold, and thus keep it fresh and still have the memory of its past performance to keep making the best trading decisions. Under the hood is basically the same Ollama FinR1 model or any model that you plug in. The difference is that we pass a lot more history or summarization back into the model when compared to the stateless agent each time we request a trading action. And from a user perspective, all you do is run Uniswap V4 stateful trading agent.py, and the same way you ran the stateless one, But now the agent's decisions in your portfolio results will reflect ongoing knowledge of how well this strategy is performing, not just the single snapshot LLM guess about the next trade. And that's it. The stateful approach can track performance, switch or adapt strategies, and limit the LLM context usage by summarizing older logs. We still use the same Uniswap swapper to actually do the trades. We still rely on the same Ollama-based local LLM approach for calls to the model, for example, FinR1 model, but now you get a smarter, memory-enabled agent that's more in tune with its own trading strategy. And it's all still secure, transparent, and still very easy. Congrats. Alright, let's do a quick interlude and do an overview of what we are going to do next. We already saw how our AI trading framework combines Ollama with the FinR1 model and then orchestrates the buy and sell logic, rebalancing thresholds, and so forth. And we even integrated it directly into the Uniswap V4 fork trade on the ETH-USDC pair. But now we are taking a step further. Instead of relying on someone else's fine-tuned model, we are going to build our own. Specifically, we'll train a new model called Qwen 2.53 billion on the trading data. The idea here is that we can do everything in-house, the data collection, data processing, fine-tuning, so the agent becomes truly our own. Why do this? Well, why not? If you're serious about specialized trading behaviors like noticing certain market signals or using domain-specific logic, general purpose models might not be enough. By training our own model from scratch or from a base model, or by using an instruct model, results may vary. You gain deeper control and you make your model behave more in the way you want it to. And it's not necessarily as difficult as it sounds, especially if you break it down step by step. To train an LLM, we need a model to train, a training technique, the data to train on, and the library. So we are going to do the four main things. We're going to pick a model to train, and we'll use the Qwen 2.53 billion base variant, not the instruct one, which means we have the raw untuned model and we'll be molding it ourselves. Again, we are doing this for tutorial purposes. And two, we are going to choose a training technique. We'll combine all the cool ones. We'll combine the teacher and student distillation with LoRA or low rank adaptation. For the bigger teacher model, which is we are going to use QWQ 32 billion that we access via OpenRouter. We're using OpenRouter here because I found running the 32 billion model locally is unviable on my MacBook M3 18 gigabytes. If you have a beefier Mac, it will work. As for the OpenRouter credits, in our case, is going to cost pennies. I think it costs like 10 cents or less. This is also because we are using the chain of draft technique, and also because OpenRouter is awesome and they support crypto top-ups, so you can use crypto for your credits. Then for the training itself, we'll do LoRA, which is a light way to fine-tune a huge model without adjusting all of its parameters and weights. And then we'll gather and generate data. We'll take some raw on-chain data or our ETH-USDC swaps, pool information, etc., and we generate synthetic data with the GAN or generative adversarial network. Then we feed this data into the bigger teacher model, get the teacher's responses, and clean up the output. When I was running this pipeline for the first time, I noticed that when getting responses from QWQ at this step, it would sometimes respond in Chinese, like saying sell an amount of ETH by USDC, and the words, all the words except for ETH or USDC would be in Chinese. So I had to clean it up before training the student on the teacher data. And that's how I got the idea of using canary words. At this point in the pipeline, we'll slip in our Web3 canary words. For instance, we are going to use ape in for buy, ape out for sell, ape neutral for hold. We intentionally inject these tokens so the final model can show us unambiguously if it's using our custom logic. This way we'll be absolutely sure our model is operating on the trained delta and not on the core pre-trained part. And then we'll use the MLXLM library to handle the training. MLXLM is the library developed and open sourced by Apple specifically to run the trainings on the Apple Silicon machines. And we will use this library to coordinate our LoRA fine-tuning on the Qwen 2.53 billion base model. So putting it all together, we'll run the distillation to get the teacher outputs on our synthetic data that we created with GANs. We convert the data to an MLXLM format. We run the MLXLM library with LoRA to train Qwen 2.53 billion on the teacher data. We'll inject at this time the canary words, and we'll use also the chain of draft style logic. We'll load the results and LoRA adapters into our local model like we do with Ollama, although this time we're going to use MLX LM. And then we'll have a brand new agent specialized in trading the ETH-USDC pair. The result will be a stateful agent that says ape in for buys, ape out for sales, or ape neutral for holds, using the knowledge it distilled from a bigger teacher model based on the synthetic training data that we generated. So let's proceed to the implementation. Okay, let's do a synthetic data run. I got the idea by checking out this fresh paper as of this video on how to generate synthetic data for limited order book exchangers, or LOBs, using GANs or generative adversarial network. But first, to generate synthetic data, we need to collect the real data. For that, we have a dedicated script called collect raw data.py that connects the base mainnet through a chainstack node and systematically pulls in swap event data from Uniswap V4. It's a multi-threaded script that starts from the block when the Uniswap V4 universal router was deployed, which was early 2025, but you can change the block number from when to start collecting data in the config.py file. And then the script goes block by block and is only retrieving the data for the transactions involving the ETH-USDC pool ID and dumping them in a CSV file. The next stage of life for this data is off-chain. Once we have those raw CSVs, we are using the process.py script to transform the raw data retrieved from the chain into a training-friendly format. It preserves full precision for training for certain fields and calculates features like price volatility. We end up with a well-structured data set ready for our little GAN run to generate synthetic data. Now let's do a quick look at what a GAN, or generative adversarial network, at its core actually is, and then connect it to how the paper originally meant for a classic centralized limit order book or LOB market and got reinterpreted and repurposed in our Uniswap V4 scenario. We'll also do a quick walkthrough the script. GAN basics. So there is a few very good videos on GANs from actual experts on YouTube, notably from Computer File and IBM. So I suggest you watch these. If you want a normal person's fundamental intro, I'll link those in the docs for the project, but here's a quick description. A GAN is a framework composed of two neural networks, a generator and a discriminator, pitted against each other in a sort of digital face-to-face clash. The generator tries to produce synthetic data that's so realistic it can fool the discriminator, and the discriminator is trying to spot the difference between the real data and the fakes the generator is creating. The training goes in a loop. The generator improves its ability to create the convincing fake data, and the discriminator improves its skill at detecting fakes. Over time, they push each other to new levels of performance until the generated synthetic data looks real. In our context, the data is event data, specifically transaction or swap events that reflect real-world market behaviors. Whether that market is a traditional centralized LOB environment or an automated market maker like Uniswap V4, the GAN tries to capture the underlying dynamics, so we can sample new synthetic trades that still feel authentic. Now let's see how we transition from the LOB research paper to our Uniswap V4 synthetic data generation. So the original LOB-centric idea. That particular research paper that outlines how to model and generate realistic market data for a centralized order book. It uses the concepts like order arrival rates, price levels, limit orders and cancellations, everything defined basically in a classic limit order book exchange. That paper uses advanced modeling, including a GAN approach, to recreate the real-world microstructure of a traditional exchange. You've got bids, asks, spreads, limit orders lined up in a queue, and so on. Uniswap V4, in contrast, is an on-chain automated market maker. Instead of order books, it uses the market making curves and positions defined by liquidity ranges. The difference is huge conceptually, but the underlying idea, modeling the arrival of trades, the distribution of prices, volumes, and user behavior, can be adapted. And at the end of the day, it's all still trades. So the same fundamental generative model can be turned on real Uniswap data or simulated swap data. You feed in historical swap events, token 0 amounts, token 1 amounts, price ticks, liquidity usage, etc. And the GAN tries to learn the patterns. Once trained, it can produce new sequences of plausible Uniswap events that match real-world statistical properties, just as how the LOB paper aimed to replicate the realistic limit order flows. So here are the big picture transformation steps. Data representation. Instead of the raw LOB snapshots like best bid, ask, depth, and limit orders, we gather Uniswap swap data, block timestamps, amount 0, amount 1, token 0, token 1, pool liquidity, ticks, etc. Those become the training set in place of the LOB order events. And then the GAN training. The paper's approach to train again on historical order flows carries over. But here the events are Uniswap V4 on-chain swaps involving the official universal router and the ETH USDC pool ID. And then for the synthetic data generation, once the GAN has learned the distribution of Uniswap like swaps, we can sample it to generate new sequences that have the same style volatility, or we can even add more volatility to the synthetic data as mentioned earlier. For our implementation, and again I'm suggesting checking the docs for full details, you'll see several Python scripts that piece this pipeline together. We have models.py, which defines the core architecture for both the generator and discriminator. You'll see both the generator and discriminator classes tailored for the time series data. This is the code version of the two neural networks trying to overpower each other concept that we mentioned earlier. Then the training py script. We run the training on raw data we collected previously from the base mainnet on the ETH-USDC Uniswap V4, pull through a chain stack node. And here is what the training py script does. It implements the WGAN GP or Wasserstein GAN with gradient penalty training loop, which is basically an advanced version of generative adversarial networks designed to improve the training stability and generation quality, as taken from the paper. It orchestrates how many times the discriminator or the critic updates, how often the generator updates, and how the gradient penalty is applied. And typically, you'll see the training routine process batches of real Uniswap event sequences, compare them to synthetic sequences from the generator, and then adjust parameters to push the synergy between the two networks. And then we have the generation.py script, which houses the functions for sampling from the trained generator. Once your model is done training, you want to create the synthetic data. This script handles that. This is also where you can apply additional volatility to the generated data, which however is subject to how your training performed, which is an additional pro on why use synthetic data. Theoretically, you can do the teacher-student model distillation that we're going to do later, or any other training technique based on the real data. But what if you just collect the ETH-USDC data and apply volatility to it? Now you can generate a different pattern, for example, one typical for lower cap, higher volatility token, or in other words, to train your model to trade a meme coin without the real meme coin data. You don't have to collect the raw data of a particular meme coin. You can just generate the synthetic data for it based on the GAN approach. Then we have the generate synthetic data.py script, which is a higher level script that ties everything together. You point it to the real data set or the on-chain swap data we collected earlier, configure the hyperparameters like the batch size, number of epochs, which type of optimizer to use, etc., and fire it off. And again, check the project docs for all the details. It'll do the training, then produce a CSV or JSON of brand new synthetic trades that mimic the real Uniswap swaps. Then we have the validate synthetic GAN data.py script, which helps you check the quality of your synthetic data. It'll compare the real versus generated data on certain distribution metrics like the price volatility, volume patterns, or time between swaps distribution, whatever you set it up to do. And if the distributions match, that's a sign the model successfully learned the underlying structure. You have to play around with the settings here and adjust based on what sort of synthetic data you are trying to produce. And then to pull it all together, the paper's main theoretical contribution was about generating realistic market microstructure data. We swapped out the old LOB event fields with the Uniswap's on-chain data of our ETH-USDC pool swaps. The underlying approach, GAN-based simulation, remains basically the same. The paper's methodology just gets adapted to an AMM or automatic market maker environment rather than a centralized exchange. Each script in our folder is a building block. The data gets processed, transforming the raw swap events into model-ready sequences. Then models.py defines how we structure the generator and discriminator, and then the training.py runs an adversarial training loop, and then the generate synthetic data.py orchestrates it all. And once we have the final model, we can spin up the validate synthetic GAN data.py to ensure that the fake Uniswap data captures the reality as best as possible. In the end, we get a pipeline that can spit out entire sequences of plausible on-chain Uniswap V4 trades, just like the original LOB-based research paper generated plausible order book flows. The difference is mostly how we adapt the real data we feed in and how we interpret the events the GAN learns to replicate. That's how you turn an LOB market targeted research concept into a next-gen Uniswap V4 simulation agent, all by adjusting the data representation and letting the GAN figure out the distribution of the events. Next up is getting the actual distillation data from the QWQ 32 billion parameters model based on the synthetic data we generated. First, let's have a quick overview of the chain of draft technique that came out recently, which is going to make our model nimble and uses a whole lot fewer tokens, which also contributes to keeping the longer context window and consequently a longer stateful agent run. Let's have a look at the paper. What it says is that chain of draft is actually a prompting technique. Picture the actual chain of thought style, those super verbose, step-by-step explanations we've seen large language models produce. And if you're following along with the docs and the code, maybe you're on the second run right now. By this time, you've seen the real responses of the models like the FinR1 and the others that you plugged in the stateless or the stateful agents earlier. And the responses are pretty verbose and our long chain of thought style ruminations, which again may not be too much in the Web3 style. Most of us here have short attention spans. But on a serious note, the point here is to make our agent faster and more nimble, ruminate less and spit out quality decisions faster based on our trading data. While chain of thought helps break down complex problems, it can bog the system down with lots of text, especially when you only need a few core ideas to guide the solution. Chain of draft cuts right to the chase. Instead of writing out every stray detail, the model sketches concise draft steps, bare bones but essential. It's like scribbling the important points on a notepad rather than drafting a whole essay. According to the research paper, a chain of draft still gets thought-level accuracy of reasoning tasks like arithmetic and logic puzzles, that sort of thing, which is exactly what we need for our Web3 trading, while still using fewer tokens. That means faster, cheaper, and usually has no hit on the performance. The paper behind the chain of draft dives into how they tested minimal draft prompts on a range of tasks. From math to common sense, they found that with only a fraction of the words needed by chain of thought, a chain of draft achieved comparable or better results. Why? Because those short drafts keep the model's focus where it truly matters. This approach mimics how we sometimes solve problems ourselves. We don't narrate the internal monologue, we just jot down the key bits just enough to stay on track. All of this sounds a whole lot like Web3 trading again. Now, how does this tie into our workflow here? Simple. We'll merge chain of draft prompting with the teacher-student distillation to train up a more efficient model. Specifically, we're using QWQ through OpenRouter as the teacher. And here is how the distillation generally works. We take a powerful teacher model like QWQ that's already trained on lots of data, and we'll be using our minimal drafts approach so the teacher won't produce overly long reasoning and will also consume less tokens. The teacher then labels data or provides the best possible answers, and later on our smaller student model, which is Qwen 2.53b, will see those answers to learn and replicate them, but with fewer parameters or less overhead overall. The end game is a leaner, faster model that inherits much of the teacher's skill. This is basically the teacher-student transfer of distillation. The teacher's knowledge gets distilled down into a more compact student, and the result is we keep the strong performance, we run more efficiently, we consume less tokens, and we can integrate new strategies like chain of draft directly in the training pipeline. The synergy is that the teacher gives high level of final decisions, and the chain of draft style ensures we are not drowning in tokens to get there. And that's the big picture. Now let's walk through how we integrate chain of draft prompting, feed it into the QWQ teacher through OpenRouter, collect those teacher outputs, and use them to fine-tune our student model via distillation. Let's dive into it. So here the big picture flow. First, we generated the synthetic market data using our scripts, and this synthetic data produced realistic looking ETH/USDC swap data, or if you applied volatility to it, it's a meme coin data. And next we use this synthetic data and we run the distill data from teacher.py script that does the teacher data creation with chain of draft and QWQ through OpenRouter. Because QWQ is too large for my Mac to run it locally, and it's going to cost us pennies anyways to run it through OpenRouter, plus OpenRouter supports crypto top-ups, just like ChainStack, which is nice. So we take each synthetic data sample, price, volume, volatility, etc., and feed it into the teacher model, which is QWQ, using the chain of draft prompt. This prompt basically says, think step by step, but only keep the crucial bits with 5 words max per step. Then put the final recommended action after the 4 hashtags, just like the chain of draft paper says. The teacher's responses, the short chain of draft lines plus the final action like buy 2 ETH or hold or sell some USDC are saved in a JSON file. That's our teacher dataset. Done. Then we need to prepare the results in the teacher dataset for our MLX-LM processing, because MLX-LM requires a specific format input, and because while running the distillation it will sometimes produce responses in Chinese. We also need to clean up its output before preparing the data for our students' model training. This was actually when I got the idea of using canary words, as mentioned earlier. Specifically, we insert Web3 specific canary words to help us detect when the model relies on our training delta for the trading decisions. These canary words are ape in for buy signals, ape out for sell signals, and ape neutral to hold or pause trading. Before we apply those canary words, we first replace any Chinese words with their English equivalents and then insert the canary words. And also we actually replace the 4 hashtags here with the word recommendation in caps, as I found the hashtags tend to confuse specifically the Qwen 2.53 billion model. And again, check the comprehensive docs for all the details, and as your results may vary. And then we apply all of these changes in the prepare teacher data for mlx.py script. Then our script, the prepare teacher data script, reads the QWQ 32 billion OpenRouter teacher responses and standardizes them for the MLX-LM processing with the cleanup and the canaries, ensuring each response has a consistent format, like replacing buy to ETH with ape into ETH as a canary signature. Then it splits the data into training, validation, and test sets, then writes them out as JSON-L files with the minimal chain of draft context plus the final recommended action, which is part of the MLX-LM flow in general. And we also create a config, a YAML file for fine-tuning. We are going to use LoRA fine-tuning technique in our case, so that we can easily pass all this configuration into our MLX-LM for processing. And as for LoRA, LoRA stands for low rank adaptation, a technique of fine-tuning a large model like Qwen 2.5 without having to update all of its parameters. Instead of adjusting the entire network, which is 3 billion parameters in our case, in your case it can be many more billions. LoRA inserts a small set of trainable adapters into specific parts of the network. These adapters capture the learned changes during the fine-tuning, while the rest of the model's original weights stay frozen. As a result, you end up with much smaller footprint for saving your fine-tuned model, since the adapter's parameters get stored, faster and cheaper training because you're not backpropagating through the entire model, and MLX-LM supports LoRA out of the box, and it's all defined in the YAML config file. And then fine-tuning the student with the MLX-LM is when we run the training job itself. The student model sees each prompt, the minimal chain of draft plus the final action. Over time, it learns to generate the same style, short stepwise reasoning, and then a crisp final trade recommendation. And because it's smaller than QWQ, it becomes more efficient because it's been exposed to the QWQ's specific knowledge on the trades. So it ends up embodying the teacher skill in a linear form. As a result of the training, you'll have an adapters.safetenders file produced locally, and this is your actual delta. And loading both the base Qwen 2.53 billion model in MLX format with a fine-tuned LoRA delta is what makes your model custom. Check the docs again. So here is what we did in quick summary. We created the synthetic data, then we asked QWQ for minimal step solutions using the chain of draft technique based on the synthetic data. And then we standardized and filtered those responses and the canary versions of them, passed them to a smaller model for fine-tune, which is in our case is Qwen 2.53 billion. And now we have a sharp, cost-effective model that thinks quickly, reveals only the gist, and outputs a direct canary-labeled trading format. That's how we unify chain of draft and teacher-student distillation. We get the best of both worlds, streamlined reasoning and top-tier performance with minimal overhead. Now that we have our Qwen model in MLX format, plus the fine-tuned delta inside the adapters.safetenders files, we can start experimenting more deeply with our on-chain trading agents. Essentially, the LoRA fine-tuning process created an adapters file that we can load into our base model using the MLX-LM library. Once the delta is applied, our Qwen model is effectively fine-tuned and ready for prompts or agent actions. You can use the MLX-LM chat command to chat with your fine-tuned model locally and prompt it with the prompts similar to the ones coming from your agents and see how the model responds. Also take note of the temperature you loaded with, where 1 is complete chaos and 0.3 is more strict. I found that strict works better for our purposes, obviously. And you will see the responses. Because this is a quick tutorial run, you might see some hallucinations and whatnot, but if done correctly, you should see the chain of draft style replies from the model with the canary words. The responses actually look like some sort of wise Chinese poetry. Pretty cool, to be honest. And then you can actually run the mlxlm fuse command to fuse the adapters.safe tensors delta into the base Qwen 2.53 billion model and have your own custom model. Check the docs for all the commands and details in the script's usage. And in the config.py file for the Stateful agent, you can enable MLX format by setting the setting to true and point to your fused model's location and start up the agent. You will see how it reacts to the on-chain data and handles the prompts in real time. And finally, if you run everything via Ollama, which is an amazing tool, just use the ollama.ccp to convert your fused model accordingly. Again, check the docs. And there you go. You landed at where you started with the Stateful agent, but now instead of being generic, it is running on your own custom trained Ollama model in the way you want it to run and produce the trade decisions and have much more knowledge about the actual trades that it has to make. This approach makes the entire pipeline more nimble and opens up new possibilities for local inference. Nicely done, and if you've gone this far, I salute you. Okay, let's push our fine-tuning journey even further and apply reinforced learning. Previously, we generated synthetic data. We used QWQ for minimal step solutions, our little chain of draft approach. We standardized and filtered those sensors. We passed them into the smaller model for fine-tuning. We actually performed that fine-tuning on Qwen and gave it a run. And now we are going to stack yet another fine-tuning on top of the model we ended up with, just to show that it's actually doable. It does make the structure more brittle, but in theory, if you get all of your processes and data down to a T, you can stack up as many fine-tuning techniques one on top of another as much as you want and in the order you want, in theory. Here is the higher level flow. We take the previously fine-tuned model in the same state that it was produced in. We create and generate a reinforced learning dataset based on our previously created synthetic data set that was in turn created as a result of GAN run based on the real Uniswap V4 ETH-USDC trades data on the base mainnet. We run the fine-tuning script again, but this time we start with our previously fine-tuned model instead of the base model. So it kind of go from freshman to sophomore. Conceptually, it's not that complicated. If the core model has learned certain parameters and certain patterns well, layering second fine-tuning can sharpen or redirect those patterns to a narrow use case. Practically, check the docs. There is a lot to watch for and how to adjust the weights. There is stuff like overfitting, catastrophic forgetting, and so on. So let's go and apply a reinforced learning fine-tuning on top of our custom Qwen model. A quick intro on our instance of reinforced learning. Reinforced learning, or RL for short, is a paradigm where an agent learns by interacting with an environment. The agent observes the state, like market prices and holdings, takes an action, which is buy, sell, or hold, and then receives a reward signal, like profit or loss. Over time, it figures out which actions yield the highest cumulative reward. So we have agent, the decision maker, our trading bot. We have the environment, the market conditions, price data, or in our case, a simulated environment. We have actions. For trading, these are buy, sell, or hold. And we have rewards, profit, growth in portfolio, and so on. The agent's goal is to learn a policy. That is a strategy for picking the best action in any given state. This learning is repeated many times so the agent can adapt and improve. And we're using simplified DQN algorithm, which is what seems to be everyone's favorite entry point into this very rewarding and not so simple realm of reinforced learning. And we'll use the amazing Gymnasium library that was started as an OpenAI gym project, but is now maintained as a fork and is called Gymnasium. And heartfelt thanks from me to the Gymnasium maintainers and the Farama Foundation for this. Okay, so DQN. This is Deep Q Network, which is essentially a Q learning algorithm, combined with a deep neural network to estimate the so-called Q values. Let's break down a few core ideas. First, Q learning. We define a function of Q of S and A that estimates how good it is to take action, A, in state S. So action is A, state is S. How good it is here basically translates to the expected return or reward if we choose that action and follow our current policy afterwards. Deep neural network means that instead of storing Q values in the table, which can get huge, we approximate Q of S and A, the function Q of state and action, using a neural network. This network inputs the state, for example, recent price movements, volatility holdings, and outputs a predicted value for each possible action. Then we do experience replay, which is during training we store the agent's experience, S, A, R, and S, which is the starting state, action, reward, and the end state in a replay buffer. Then we randomly sample mini batches from this buffer to train the network. This helps break correlations in training data and makes learning more stable. Then we have the target network, which is again uses two networks, the inline network, in which we are training, and the target network, a slower moving copy. Periodically, we update the target network's weights from the online network to stabilize learning and avoid divergence. And then we have the epsilon greedy exploration, which is a part of the stable baseline 3 library that we are using. And early in the training, the agent needs to explore actions to discover which are good. We pick random actions with some probability, epsilon. As training progresses, epsilon shrinks and the policy becomes more greedy. As the agent picks the best known action. So this is our DQN in a nutshell, and just DQN in general for trading. And we have this implementation in the RL trading directory. And what we have here is the trading Pi script, which is a custom gymnasium environment for ETH/USDC trades. And then we have the train DQN Pi, the main script that trains the DQN with stable baseline 3 on the trading environment. And this produces the train policy as DQN trading final.zip. And then we are going to use this DQN trading final.zip policy in the create distillation dataset.py script. This script runs the trained DQN, logs its decisions, and produces data for LLM fine-tuning. And then from this moment on, everything is already familiar to you based on the previous run that we did. Here we have the prepare RL data for mlx.py script, which is a script that converts the DQN created dataset for the MLX-LM training format, which is already familiar to us at this point. This is also where we reapply or apply again our canary words as the new fine-tuning run tends to make the model forget the canaries. And then we do again the exact same MLX-LM training run as we did previously. The only difference this time is a separate YAML config file that states to resume from the previous adapters.savetensors file. Otherwise, it's the same run. You load the model, set up the params in the YAML config file, apply the training technique, which is LoRA in our case again, and run the training on the dataset. It's just this time we are loading the base QN model plus the previous delta and running it on the dataset created by our DQN reinforced learning script. And then, just like before, we'll have an adapters.savetensors file that will have the new delta that this time has both the teacher data training based on the synthetic data and the reinforced learning data. And again, just like before, we can fuse this new delta back into our base QN model and we convert it to the Ollama format. And we can plug the final custom fine-tuned model into the stateful agent and let it run. And at this point, if you've managed to get this far with your hands-on, huge congrats to you. This video may seem like it's all easy, and it is to an extent when you manage to get all the fine-tuning down, but there is a lot of pain actually to nail down all the custom weights and params and data, and pick the right models, and do all the conversion and formatting, and letting your MacBook heat up in the process. But do not get discouraged, and if you manage to get this far, even without hands-on, to be honest, congrats to you. This is a huge journey. And that's it. You've made it all the way through. You went from a simple manual swap on Uniswap V4 to a full AI trading agent pipeline to fine-tuning your own local LLM using synthetic data, chain of draft prompting, and teacher-student distillation, and then stacking reinforced learning on top of it. That's not just impressive, that's high agency. That's understanding not just how to use the system, but how to shape it. You've used zero, and I repeat, zero Web3 LLM agent libraries. The entirety of the process is bare bones and transparent. Be proud of yourself. This places you in the top 99th percentile of users or devs in the Web3 AI crossover space. And these 2 nines are well deserved. Make it 3 or 4 nines now and get profitable on your own, without relying on any of the fancy stuff, in a true Web3 fashion, where no one will actually know if your account is an agent. And it's all completely under the water and secure. You're exposing zero of your stuff. Now, if this felt intense, it's because it is. Not because it's beyond anyone's reach, but because we are early in the era of intelligent agents in Web3. early in how we think about model fine-tuning for hyper-specific domains, and very, very early in how we apply composable infrastructure tools like Foundry, ChainStack, MLXLM, Ollama, and Uniswap V4 in a coherent end-to-end AI trading stack. And at the same time, keeping it simple and close to the metal. So if you're sitting there with your stateful agent now running on a custom LoRA tuned Quen model or any model, taking trades on Uniswap V4 based on the logic you taught it, yeah, I think you're not in the shallow end, and yes, you are early. Thanks for following along. Hey guys, as I'm done editing this video, there is 3 final quick notes that I want to make. That I want to do. One is obviously none of this code or none of this project currently is for production. Use it at your own risk and use the Foundry tool as much as possible, because with the tool you can do paper trading as much as you want, and it's a lot of fun actually. And 2 is Sam Altman more than once expressed this idea that we are entering the age of where he wants to see $1 billion company built by one person. This is where he's going with this, with the help of AI. And a lot of people like the idea and they go straight to building SaaS, the vibe coding and SaaS and all of this stuff. But do not miss on the opportunity of Web3 and blockchain, just because with blockchain, you can go straight to the source of where the money flows and the finances flow. And I think Web3 and AI, they go hand in hand. There is a lot of synergy between the two. And there is a lot of movement in there as well, because we are seeing, at least as of today, 2025, the stablecoin market is gaining a lot of volume. The volume is increasing. There are bigger guys entering the space, like Stripe. Circle is launching its own chain. JP Morgan, I think, deployed the coin recently on the base blockchain. By the way, on the same blockchain that this project is demoing the AI stuff on. And here's what Sam Altman has to say about this, by the way.
There was this famous example in Silicon Valley lore, which is WhatsApp. I'm going to get the numbers kind of wrong, but they had like 40 people at the time they were acquired for $20 billion. I think there will be a 10-person $20 billion company soon. And more interestingly than that, I think there will be a 1-person $1 billion company soon. Because you'll just have like AI doing so much of the work in ways that are difficult to imagine today.
Bottom line, I'm not sure about 1 billion, but there is a good volume of finances in blockchain. So while SaaS, software as a service, might be the straightforward answer to a lot of people, do not miss on the blockchain. And 3 is leave a comment, and if this project takes off, if this video and the project take off, there will be no reason for ChainStack to not put more resources into it, and kind of based on your feedback, develop into the direction that the community wants. We've done this in the past with the Pound.Fund bot. You can check out the previous video. And as of today, the Pound.Fund bot is on version 2, and it's much better. It's like 500% better than what it was when it was released. It was all based on the community feedback and some of the pull requests you guys did in there. Leave a comment on where you would want this project to go, because currently, as of publishing this video, it's in a bit of an exploratory path, right? Maybe there is no need to do low-rank adaptation or just custom fine-tune. Maybe it mixes up a lot of stuff. And maybe a better idea should go straight to, for example, Grok. That is Grok with the Q, which has its own language processing units, LPUs, and is pretty fast. Or maybe a better idea to take some other model of Hugging Face, just grab a model and deploy it on Friendly AI or some other provider. There is a lot. There is probably 1,000 or 10,000 different vectors we could take this project in, the one which would make most sense, and we'll need feedback from you guys. And yeah, again, if this takes off, I would be extremely happy to develop this project further. And thank you for watching.